All right, in this video, we're going to talk about the alkenes and the alkynes, which are the unsaturated hydrocarbons. And so in the previous video, we went through and we created this sheet and we looked at a bunch of different varieties and ways of doing the alkanes, that they can all look basically different, but it's really the same thing. These are all heptanes. And the key thing about the alkenes is they're all single bonds. Where we get into the alkenes and the alkynes, now we're going to be dealing with a double and or triple bond. And so we still need to follow the same prefixes or same numbers. And so if we just focus on, we'll use the same one again. Let's go with heptine. And we could do heptine as well. Just make sure I spell it right there. And the key thing with the double and triple bonds, or the alkanes and the alkenes and alkynes, is that you have to make sure that you number and or basically label where that double or triple bond exists. And so if we do hept, again, hept is going to be 7, so we'll keep it simple. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Just make sure I got them there. Now, there's different places where I can put this double or triple bond, but we only have to give the numbers the lowest numbering system, or the only thing we should do is give the lowest numbering system for this material. So you got to remember, these things can flip upside down and turn around. And so if I'm looking at this structure right here is the same as I turn it around, even though it looks different. Now it looks like it's curved this way instead of curving this way. It's still the same molecule, it just turns around. And so the same thing can happen with these, with the double and triple bond. I can have my double bond right in the beginning, or I can have my triple bond right in the beginning. And then what we need to do is fill in all the hydrogens. Now remember, each carbon needs a total of 4 bonds. So this carbon already has 2, so that means I need to put 2 more hydrogens to fill it in, because again, the rest is just going to be filled with hydrogen so that each carbon has 4. This carbon has 2 to the left and 1 to the right, so that's got a 3, so that only needs 1 carbon. This carbon only has 2, so it needs a hydrogen up and a hydrogen down. Same as these, we basically have that, again, homologous series where it's the same, it's repetitive over. And then this last one only has 1, so I need to add 3 hydrogens in here. Now, the formula for alkenes, as we said in the previous video, CnH to the 2n, where the alkynes is CnH to the 2n minus 2. And so we're just going to show you that. If you remember, the alkane formula was 2n plus 2. And again, these are all on table Q. Your formulas are right here on table Q in the New York State reference table. So you don't, if you forget, if you're freaking out in the exam, use your reference table. Remember that. Alkanes, 2n plus 2, and we went C7H16, so we'll come back to that in a minute. If we just look at this, so we know we have C7 in both cases, but let's look at this one first. I have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. And so that follows the formula of CnH to the 2n. I took 7 and I doubled it. 7 times 2 is 14. And so anytime you have an alkene, if you were just counting to figure out what it is, you could actually look at the formulas to see, or you might get a series, you might get a question on the Regents exam that says, which 2 examples are alkenes? And you have to look at the ones that are doubled, okay? If you get something like this, C3H8 and then C7H14, those 2 are not. This one is doubled, but this is not doubled. Okay, the doubling of this, propane, would be C3H6, not H8. So let's look at the heptine. This one already has 3 bonds to it. It's got the triple bond, so it only needs 1 more hydrogen. Notice the beginning parts, this has 2, but this has 1, so I've already changed the structure some. This one, notice here, this is a crucial one that you pay attention to, because we cannot give more than 4 bonds. It already has 3 to the left, 1 to the right, so it does not need any more. But these next ones all have 2, so they need a hydrogen up and a hydrogen down. Again, the drawings don't have to be perfect, but you need to make sure that you account for each of those hydrogens. And the last one already has 1, so I just need 3 to end it. If we count, there's 1 at the end, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Notice I went from doubling to doubling less 2. Okay, 14 minus 2, of course, is 12, which is what our formula shows. Cn, n would be 7. 2 times n is 14. 14 minus 2, of course, is 12. So when we're drawing and we're looking at our structures, alkanes and alkenes and alkynes, we need to make sure if there's all single bonds, if there's a double bond, or there's a triple bond. If we bring up the propene, if we do propene, for example, of course, I can only put the double bond here or here, okay? It only can be one place or the other. Same thing with propyne, but if we do this, notice this already has 2, so it needs 2 more. There's 2 hydrogens. This has 3 bonds, 2 to the left, 1 to the right, so it only needs 1, and then this one needs 3. So I have 1, 2, 3, 4, 5, 6. Remember a few minutes ago we said it would be C3H6, and there we go, okay? So we've doubled the hydrogens in that formula. Now, a few minutes ago I talked about where we can put this. Now, for this one, it shows that I can only put the double bond here or here, so it doesn't matter if I turn it backwards or forwards, it's still the same thing. But if we take a look at either one of these, it doesn't really matter which one we use because the concept is the same. If I take my 7, and we'll do one with the the alkenes, and we'll do one with the alkynes. Let's say I put my double bond here. Okay, now it's somewhere in the middle, and whether it's here or here, it doesn't matter, that's the same side. Because if we start at the end, if we come in 1 and then come in 2 and then come in 3, it really is the same thing, just flipped around. So we really need to number these. And so what this first one here, this one would technically be 1 dash heptine. We would have to call that 1 heptine, just like we would have to call this one over here 1 heptine. The number tells you where the double bond or where the triple bond starts. Okay, it tells you what carbon. So this is carbon number 1. This would be carbon 2, 3, 4, 5, 6, 7. Again, carbon 1, 2, 3, so on and so forth. So if we were to count 1, 2, 3, versus if we counted this way 1, 2, 3, 4, where that double bond starts, does it start on the 4th carbon or the 3rd carbon? We want to give it the lowest number. So this would be 3 heptine, or heptine, excuse me, because we're going to do a double bond, heptine, where if I had this one here, let's say I put it over here, let's put my triple bond right there. Now, a lot of people would just start counting and say 1, 2, 3, 4, 5. Sorry, you're off the screen there. 1, 2, 3, 4, 5. That would be wrong, because remember, this molecule can flip and turn upside down, just like I was talking on this previous diagrams. This molecule here, it's still the same molecule, I've just turned it around, but it looks different, right? So these molecules, we have to number both ways to figure out which gives me the lowest value. So I could go 1, 2, 3, 4, 5, where it starts at 5, or I can go 1, 2. This instead is going to be a 2 heptine, because the triple bond is on the 3rd carbon, or excuse me, the 2nd carbon. Okay, the triple bond starts on the 2nd carbon, so it's a 2 heptine, not a 5 heptine. 5 heptine does not exist. Okay, it would not be accurate to write that. Now, as far as filling in all the hydrogens, again, every single hydrogen, or excuse me, every single carbon needs 4 bonds. If you notice, these 2 in the middle both have 3 already. There's 2 with the shared bond and then 1 on each side. So each one of these needs a hydrogen, and what you'll often see is they're oppositely spread. So now if we look at this, there's 1 to the left, 1 up, and then 2 to the right. This one has 2 to the left, 1 down, and 1 to the right. So they each have 4. These 2 only have 2, so they need 2 more. Same thing with this one over here. It has 2 bonds, so it needs 2 more. And then both of my ends need 3 more, just so that they can make that value. Now if we count them all, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So again, we have the same formula again, C7H14. So the formula is fine, but notice the difference in structure. Here we have a big open area, or more of a gap at the end. Here we have gaps in the middle. So there's going to be a different structure, and therefore they're going to have different properties and different functions. Same thing holds true with our triple bonds. Notice again, these already have 3, and then they have a 4th going this way, so I don't need to add anything else to these 2 carbons, but my last one has 3, or excuse me, has 1, so I need to add 3 more hydrogens, just like this one. The ends always typically get 3 more. The ones in the middle, if they're single bonded, usually get 2 more. So we're going to put 2 on each of those. And let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And again, C7H12. So if you're given the formula, you should be able to write out where that is. But if you're just given the formula, if you're only given C7H12, you don't know where that triple bond goes, but you should know that it has to be a triple bond somewhere, because that's the formula for an alkyne. H to the 2n minus 2, that's how that would calculate. And so you would have to be given either the information, you'd be given this name first and you'd have to draw it, or you'd be given the formula and you'd have to name it. And so again, the process still would fall under using table Q and table P, looking at how many carbons are there or looking up the prefix and actually drawing. So doing alkanes, alkenes, and alkynes when they're straight up and when you number them should be pretty straightforward. Again, with the double bonds and triple bonds, you have to label or you have to draw where that structure is going to be. So for example, if I said, 4-nonine, known, 4 is going to be where the double bond, or triple bond in this case, because it's a Y and E, so I know it's a triple bond. Known, I'm going to look up, is the prefix for 9. So I'm going to do my 9 first. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's after the fourth. It doesn't matter if I count left or right. I just have to go the fourth carbon in. It's easier just to go left and right. 1, 2, 3, 4. That means it starts on the fourth carbon. Okay, so the fourth carbon in is where it starts. That number tells you where the double bond starts. So for example, we did 1 heptine first because that double bond started on the 1. We did heptine first. We did 1 heptine because the triple bond started on the first carbon. But over here, the 2 heptine, the triple bond starts on the second, because again, we can count left or right, right or left. 1, 2, 3 versus 1, 2, 3, 4, the lower number. You want to have the one with the lower number. So this is 3 heptine. For 4-nonine, if we counted the other way, 1, 2, 3, 4, 5, that really wouldn't benefit us. Again, filling in, I'm not going to continue. We're already 12 minutes into this, but I hope you understand the point that this would be the basic structure of what you would need to draw, for example, if the state required you to draw it. And then, of course, it always is beneficial to understand the amount of hydrogens. These 2 would not need any more because they already have 4. These 5 would need, because they only have 1 going left and right, they would need 2 more up and down, and then your ends would have 3.